Okay, so I'd like to present Pyg4ometry. The name was taken in PyPy, so I just put the 4 in there, associated with Gian4. It's a Python package to manipulate Monte Carlo geometry. This is a bit of a hybrid. It's half of the presentation is PowerPoint and half is a notebook, which I'll switch to halfway through the presented slides. So these slides are best viewed as PowerPoint and not as PDF for reasons that become pretty obvious when you get into the talk. So I'm Stuart Booger. I've just recently moved to the University of Manchester. For my sins, and I'm an accelerator physicist, not a high energy physicist. Okay, so please be gentle with me. What is Pygeometry in a nutshell? It's basically a Python API for GDML. Okay, now GDML is a markup language for geometry, which people can use, but I think it's an API for geometry in general, with the ability to create 3D surface meshes. So it seems like a pretty simple thing. It's something that's quite convenient, but it allows you to do quite a lot. And hopefully via this presentation, I'll be able to show you what that is. The API actually matches very closely to Gian4, the Gian4 C++ API for creating detectors. Just lowers the cognitive load on users, and I'm not a fan of writing detailed documentation, so constructors and so on for creating geometry are very similar. The primary reason was around 5 years ago is just to avoid my users, which are mainly an accelerator domain, to write geometry or input by hand, which is a really error-prone and a complex process. If you're writing GDML or some other description language, XML, you can write some tools which simplify that process, maybe which check it, but how far can you go by having a nice Python package that wraps in a nice way, the way that we tend to build detectors or other mass inside a Monte Carlo transportation code. An amazing amount is possible with a simple API. So I start that with a nutshell and I end on that point, but you'll see the examples in this presentation. So there are two really sort of main developers. A flattering picture of me from some time ago. So I'm currently the director of the Cochrane Institute for Accelerator Science. So really, I'm an accelerator scientist and do those types of things. And my co-developer, who's done this, is Laurie Nevey on the right, is a staff member, background in accelerator beam instrumentation and lasers. And so he develops a code called BDSim. So why we started all of this, we write Gian4 Monte Carlos and FLUKA Monte Carlos of accelerators. That's absolutely critical for radio protection, backgrounds, this kind of stuff. So this was started in Royal Holloway, University of London. And, we want to build these accelerators quickly. We don't have the luxury of building a geometry and having it persist for a whole run, for a long time, and for that to be refined. We often want to build up a geometry as quickly as possible and then take it down again. And so in Gian4, it's possible to, using the C++ API, to construct a moderately realistic simulation of an accelerator. And so on the left, at the bottom, is a medical accelerator. So there's a rotating gantry. You can see it in perspective. So there's a beam line from the right-hand side over here that comes from a cyclotron. It's transmitted through a beam delivery system and it's delivered to a patient via this rotating gantry. And so this can all be parameterized, but of course it looks like a Lego accelerator. And that's about as far as you can go without delving too much into a particular application domain, be it a medical accelerator or the LHC or something like this. So this, zooming in a little bit, our task was to put more realistic geometry in our Gian4 models quickly. And so we have a couple of quadrupoles here on the left, 3 quadrupoles, a bit of a beam pipe, but the question mark represents some more complex geometry, which endows the simulation with more realistic simulation. So, you can start with various things. So, for example, loading CAD files and having workflows where you load CAD using tessellated or triangulated, let's say, geometry. And so here's an example of a medical accelerator again, where we start, replacing that question mark or that parameterized geometry with something which is significantly more realistic. So on the right, And the top, you actually see renders from Pyg4ometry, which I'll be showing you in a bit. It's a dipole magnet, which is the full engineering. Well, actually, it's not fully. There's no cooling manifold. There's no current delivery. So it's already stripped back significantly, but significantly more complex. And this can just be inserted into a model. CAD has a slightly different grammar for constructing geometry. So typically, people will talk of parts and assemblies. A part is like a logical volume. So you can have many parts and they can be assembled together into something slightly larger. And so there are loads of tools to do this, and everyone has a different workflow, but can we bring, this is one very definite example of how you could use tools like this. This is not optimal for Monte Carlo tracking, just loading tessellated geometry. This is not great. This is slow, it's cumbersome, it's error prone. Any hole in this mesh is problematic because it will cause tracking errors in your Monte Carlo. So if it isn't watertight, manifold, I think it's the correct term, then this will cause a problem. So there's a lot of checking that needs to go into these generated meshes, and Pyg4ometry offers tools and functions and algorithms to do all that. So accelerator physicists are also user of tools like GAN4. There's other tools too, which are less common in the HEP community. So MCNP, FLUKA, FITS, very similar. Other tools like DD for HEP or Root, TGO, don't work well in the context of accelerators. The degree of persistency that's required, the fact that they're used for calibration and reconstruction is not really important in this area. And there are diverse users of GAN4, which are really not at the same sort of skill level as the HEP community. So why? A parametric geometry interface, an API based on Python, allows algorithmic generation of geometry, stable, complex manipulation of geometry. I touch on the surface of that, of what's possible in the notebook. The conversion between different geometry formats beyond naive scripts, which maybe do simple manipulations, really understanding the geometry format and being able to manipulate it for different usages. Sustainability. So this is the idea that we have a long history of creating different detectors, and we may be receiving information, geometric information on detectors from different sources. Feature extraction. So with quite a powerful geometry library, we can extract features from geometry which are useful to us, and just new fun applications. So I've got an example of augmented reality. The potential users are HEP detector physicists. I would say less so the large detectors, but those making small prototypes who want a rapid turnaround in their simulation. HEP simulation developers, so for example, those making interfaces with optical ray tracing codes. Of course, radio protection, space weather, medical physics, and nuclear physics. This is kind of the wider range of GAN4 users than just the HEP community. The requirements which are evolving is to load and convert GDML, STL, which is tessellated format, STEP, a CAD format, FLUKA, root files, and just be able to load and write those, and then in between, while the geometry is loaded in memory, execute changes. So this really means supporting the complete reading and writing of GDML without modifying the file or doing anything in between, to be able to visualize that, to check for overlaps and potential geometry issues, to do the compositing problems, to load lots of different geometry in from different sources and be able to run a simulation, rendering for data analysis. So modifications could be cutting holes, removing or changing materials, clipping the outer volume. With that came a certain set of thoughts. So leverage modern tools and programming, lightweight, open source, simple to use API. So for use, I think the API is simple enough for a summer student, simple enough to contribute to. Think of a PhD student. Reasonable performance, not the ability to render a huge GPD, general purpose detectors, but to be able to do things quickly in this space. So really it follows GAN4 as much as possible. So follow the sort of patterns and style of GN4, so in terms of object interfaces, methods, and internal data. GDML is chosen as a fundamental file description of geometry, and use existing code libraries wherever possible. So we aim for 100% coverage. We're at 72% right now. And we could really just create Python class representations for geometric data and other data too. So on the left, you have lots of different sources, be it GDML, FLUKA, step. The user can input code and control PyGeometry, and then you can export it to different targets. Right now, FLUKA and GN4, GDML are there, but we're just about adding MCNP and PHITS, which are other Monte Carlo general purpose Monte Carlo transport code. So this is what it is. So it's the glue in between to be able to execute this. The technology tools and dependencies are quite a lot. So it's of course all based in Python, hence this presentation. It uses ANTLR to understand the input file, the GDML input file. So, and this in GDML, you're allowed sort of mathematical expressions, and I'll give an example of that. The rendering is done in VTK, so this is the Visualisation Toolkit. To do CAD loading, there's a great open source CAD library called OpenCascade, which is available. And to do complex geometric algorithms, which are required, CGAL, the Computational Geometry Algorithms Library, is used. Now, bindings exist for these two packages, very complete, very large bindings into Python. I took a tack of only pulling a subset, which is required, and developing PyBind 11 interfaces to both of these, which I don't know is maybe a good choice, maybe not. And then on the side, sometimes relevant is SymPy for producing and simplifying some of the geometry at various stages. So it could be SymPy could be used on input on ANTLR, where there's a complex mathematical expression that can be simplified. It also is useful for converting into FLUKA geometry, because you do end up with quite large mathematical expressions which can be simplified. So there's smatterings of SymPy in there. Okay, legitimate questions before I get into the next parts of the talk. So why not just write C++ using GN4 API? It's heavy. The compilation cycle is comparatively long. It's hard to debug geometry in some instances. So I'll give you an example. For accelerating Monte Carlo tracking, typically the geometry is voxelized, and make a little voxel to accelerate queries on the geometry, but that will crash because of overlaps. So, but how do you find the overlaps in your geometry? Okay, so there's a chicken and egg sort of situation there. And you just want to be able to quickly see if your geometry makes sense and agrees with your experiment or your test stand. Why don't you just include this functionality in root? It's really about the user community where I came from. So not all users of GN4 are particle physics experts. It's hard to prototype in root. And I would say scripting languages are quick for early career researchers to pick up and use. Lots of packages exist with Python bindings and can be collected. It's quite straightforward. Why don't you just expand GN4? This has already been done. So there is now a VTK viewer and in GN4. And CGAL Boolean processing is already implemented and performs well. So this is actually a little bit of a forge. This PyGeometry has turned out to be a little bit of a forge for testing ideas, which would take a reasonable amount of time to implement in a code like GN4. So it's a nice little test utility, which is then very, very handy, but then can also support the development of GN4. Why don't you just write GDML? It's quite hard to debug. I've tried 6 years ago to just write it and see how that went, and it wasn't great, and I didn't have a great experience of understanding where I'd introduced bugs and so on. So now I'm just going to switch tack a little bit and just go through Jupyter Notebook. So hopefully you got a flavor of what is going on here with PyGeometry. I'm just going to switch. So hopefully everyone can see my Jupyter Notebook. Please let me know if you can't.
You can see it, yeah.
So apologies. this requires quite a lot of OpenGL. And although I've got it working in Docker instances before, Docker containers before, it didn't work in my attempts leading up to this meeting. So I'm running this one on my personal computer. If you have a line and you're following, which is this view line, this is invoking all the graphics and OpenGL, and that will crash. Okay, if you install it locally on your machine, it should work fine, and it's something that I think I just need to work at. Okay, inlining into a Jupyter notebook various 3D interactive 3D windows. There's a real diversity of solutions there, and I haven't quite got it working. So if you're trying to follow along and your kernel crashes, please just comment out any line that looks like this view line, and it will work, but of course it won't give a nice rendering. I will inside this notebook there are screenshots of what should be seen. So just starting, so just importing Pyg4ometry. Now, GDML and names in geometry typically are a global namespace. So they have this, so you just have, detector or box or world, and that encompasses your detector. And that's really difficult for name collision within a namespace. So if your task is to bring in geometry from lots of people that are building subcomponents and engineers or whoever, PhD students who are all contributing to a description of a test setup, it's quite problematic allowing people to use their own names. Of course, we can't restrict the names they give various solids or materials or optical surfaces. So part of the design of the package is to have a global registry. It's not global. It's not. You can instance this object called a registry, and that does all the bookkeeping for saving names of different things, different objects, geometrical objects. But we'll have a look as we go on. So there's this registry object, and it's really just stores everything that will go into a GDML file. Although not necessarily, I clear it because there could be some execution. People could be taking cells in different orders, and so if you have simple names for objects and you typically reusing them, then that becomes quite problematic. So just first things first, let's just create a couple materials. So here, these are NIST materials, which are defined by default in GAN4, and this is a very similar interface. So usually in the construction of anything associated with Pyg4ometry, it's a pretty straightforward constructor, the name that you're searching for in the NIST database, and then this registry. And so this material then is added to this registry. So it's a very simple geometry. There's a world and there's a box inside that world. The world is made of intergalactic gas, and the box is made of gold. So very straightforward. Then this is very traditional. If you're used to making GAN4 geometry, we can make two boxes. So here there's the world solid, which is a box, and it's 100 millimeters on edge on 3 dimensions. And there's a box placed in. There's a blocks that I intend to place inside, and that's 10 millimeters on edge. And again, this registry appears pretty much everywhere. Then, so we've made materials, we've made some solids. Let's create some logical and physical volumes. So logical volumes are the sort of prototype object. It has no placement in real space. It's just material, electric and magnetic fields and other attributes, and that can be placed many times or instanced into the geometry, and that's a physical volume. Okay, so these are very similar constructors that you find in GAN4. So a world logical volume as a Pyg4ometry constructor, which looks exactly like GAN4. So it takes the solid and it takes the world material and it's given a name. So almost everything is given a name, and hence this name collision problem. We'll make a box logical. So this is an idealized box, which is made of the box material and added to the registry. And then that box can be placed, but with physical volume, and that takes 3 rotation angles and 3 positions, the logical volume, the name of the physical volume, and the logical volume that this physical volume is placed into. Okay, so this effectively sets in. Some people will call this a scene graph. It's basically an instance hierarchical graph of the geometry, and so that is a really simple example, and then that can be visualized. So on my machine, this will run. Oh, hopefully. Oh yeah, it is here. Oh, is it? Okay, no, maybe I made an error. Okay, okay. So here, this is the VTK window. I'll try and move it a bit slower. And the rendering here is in the notebook. So this is VTK, and it's taking that geometry. It's actually a triangular mesh. So you can, if you switch view modes, this is in wireframe, of course, to solid, and you can tailor the options. You can remove surfaces and so on using Pyg4ometry. So here, that's a very simple geometry just created. In this version, where I have an external GL window open, it hijacks the input threads. And so to exit this interaction, I just have to hit Q, which I've just done. So this is now non-responsive, but it's returning me to the notebook. And so examples like this, I've put the screen grab of what it should look like when it's running. So to create a very simple geometry, it's very simple. It's actually easier to write the GDML in this case. Okay, but why? So why do this? It's very easy to write this to GDML. So we just construct a GDML writer. We add the detector, which is then the whole registry of information, and then we can just write that as GDML, and that will just be written to disk. And so that's here. So overall, very simple, a really simple API, not too much to learn, not too much to do. But one of the a good feature of GDML is to have constants or quantities or various parameters which are defined in a file, and they can be modified and calculations executed. So, for example, differences or mathematical calculations can be executed. This has been wrapped in Pyg4ometry, so I'll just re-execute this, and so we can make a constant which has a name. Again, has to be added to the registry, so we can listen. We can add this dimension that we had previously, so this 100mm world box size, and we could have another constant. So the world size is 100, and the box size is 10mm, and so we could use those in place of real parameter of floats, let's say, within Python, and Pyg4ometry responds appropriately. So here's the compressed example I had before. And so I make my materials, make some solids, but now we just replace these dimensions with world size and box size, and create a very similar structure, and then visualize that. So no change, no real difference there. Exactly the same example. But we could start making this a little bit more complicated. So we could say that the box size is always 20 times smaller than the world size. So apart from the very verbose names that we put here, ultimately it stores the computation, not the final float, and so it preserves the order of computation and uses something like ANTLR to parse this simple mathematical calculation. So taking that a little bit further, here's a sort of more substantive example. So everything here is as we've had before. So create some materials, create this world and box size. So a world at 200 and a box which is 20 times smaller, and then create a variable here, which is a ring radius. So just want to place these boxes in a ring, and then create the structure, but then place lots of physical volume, place lots of instances. So here I can create a constant, do a calculation where I've overloaded various operators so that this is actually executing not a normal floating point calculation, but wrapping symbolic calculations for evaluation later. And so we could do something like this. Look at some x and y coordinates. So resolve in cosine and sine sense a ring, and then place those in the real universe. And so not particularly complicated, but then just executing that gives you a nice geometry where all of these things are placed very nicely and very neatly. And what's not done here, and when we write this, I'll just write that geometry and view it. Ooh, hopefully, oh, actually, sorry, I've got to quit this renderer. Is that all the constants are preserved in the final file. It's absolutely no problem to be able to read these things and just bake or evaluate these calculations. So baking the calculations out when writing, or just or reading or evaluating on input. But here they're really preserved throughout. So the ring contained 20 different items, and those constants are then written, and then they are used then in calculations here later on. And it gives the user the ability to understand the formulation and the construction of that GDML in a much better way. When these numbers are just computed in, say, a Python interpreter and just output, there's no possibility. It's a bit verbose, and the SymPy is usually there, although I've switched it off to disable these brackets and to simplify these expressions. Those will be preserved into the final calculation, and they will be preserved on reloading this GDML back into PyGeometry. So you never lose the state of the geometric construction. And any work that goes into parameterizing a geometry is not lost in transmission to another user. Okay, so that's explaining some of the reason as to why. So we can parameterize and manipulate geometry. Just a little bit about editing geometry, and I just have a few examples and how it's built. So in Monte Carlo geometry, we have solids, materials, optical surfaces, logical volumes that can be stored in flat dictionaries as key value pairs. Everything has to have a name, so that's okay. The structure, logical volume, physical volume hierarchy, is stored as a multiply linked list within the logical and physical volume object. So, which is pretty much how GAN4 does it. So just here, instead of recreating all the examples, I'm just going to read the box example like we created at the beginning of this notebook. So we have a GDML reader, we just read that, and then from that reader, we get the registry. So that pattern is replicated quite frequently. Inside the registry, there's just a bunch of dictionaries, which are boringly named solid dictionary, and it's the world solid, and it's a box, and is built of various expressions. We can look at the materials, and so this is a dictionary of all the materials. So G4 galactic is made of hydrogen with two isotopes, and so that's fine. So given that we have to have a global namespace for all the objects we put in, it has to go in there, and we can then interrogate that and change things based on that registry. So we can just go in and change a solid if we like. You can actually just take one of these solids and then start changing it. Actually, solid dict, and I think it's okay. All right. Being too optimistic with my remembering my own interface. So, but we could just manipulate this solid as we like. It's a little bit different for the hierarchy. The hierarchy of logical and physical volumes is stored within the objects, and it isn't directly represented in this flattened registry. So, okay, so each logical volume and physical volume is stored, but the relationship between them isn't obvious. So Inside the registry, there's a logical volume dictionary and a physical volume dictionary, and we find what we expect to see, which is a box and a world for logical volumes, and for a physical volume, the placement of the box inside the world. But it's not entirely obvious how this detector is constructed. From the registry, we can get the world logical volume, and then it's stored in a very simple structure. So a logical volume will have daughter volumes, which are physical volumes. And so, of course, looking at the world logical, we put one physical volume in it, which is box physical. Okay, that's great. And of course, that daughter volume is a logical volume, and that can then store lots of daughters. So you would have some kind of nested hierarchy like this. So logical volume, which always starts with the world, then a physical volume, which is the first daughter. That would also have a logical volume, which then could store many physical volumes. And that tree can go on and just be terminated at the end with logical volumes. So to simply navigate, and of course this can be done in multiple different ways, you can take the top level world logical, get the first daughter volume, and then get the subsequent logical volume. And you can, of course, you can navigate that way down, or you could write an algorithm that walks the geometry to discover a volume or change things. The logical volume clearly has a solid, and this is accessed in a sensible way. And as I said at the beginning, it's just an API for geometry and meshes. And so here you can get the mesh associated with the world logical volume, which is cubical. And I just, for ease, I print the bounding box, which is a very useful algorithm for understanding geometry. There's a note here: when editing geometry in memory, changing solids or placements, the geometry needs to be explicitly remeshed to keep the geometry consistent. So this mesh object needs to be updated, associated with changes that you may execute in the Python. Otherwise, it's a lot to track, and it can be quite complicated in the dependency graph within the geometry. And so so once the geometry has been changed, there's a method world logical dot remesh, and then it rebuilds all the geometry associated, all the meshes associated with the geometry. So now a little bit more quickly, we can import other formats just to show this functionality. I'm going to put this line, which would have crashed to some kernels, some people's kernels. So it's just a simple function that just displays a solid. It's really just assigns some materials and places a solid in a world. And so we can PyGeometry has an STL loader, which is a moderately common format, and of course the classic proto geometry is the Utah teapot, which I put here. So this is now loaded as a G4 tessellated solid, and could be used now and then just written as GDML and exported. Also, there are loads of algorithms to simplify this mesh, to discretize it, to voxelize it, to run a Delaunay optimization, and so on, to tetrahedralize, and that's all given by CGAL. So maybe an application would require a tetrahedron mesh of this teapot, and this can be done with a few lines of code. Here, I just display it as the raw file as I downloaded from the internet. So quite simple. It's also pretty similar for CAD. CAD shouldn't be considered as just a format where a single object can be loaded. It has its own internal structure of parts and assemblies, which is also represented in PyGeometry. So a part or an assembly can be loaded, and if that part is used over and over again in the geometry, it can be instanced in the same way. So that is placed in the geometry, but whilst only pointing to one original piece of geometry. So here's just an example, pretty similar. Again, this is Python OpenCascade. It has a reader which reads a step file, and of course at the root, like there's a world volume in a detector, In OpenCascade, they're called free shapes, and there could be many top-level objects which are the top level of the tree, and I just get the first one starting, and then take this and convert it to a tessellated GN4 object. So again, you should see something like this, and here there are some primitives I wrote in Fusion 360, an Autodesk product, and these are the simple CAD pieces that you could load. Clearly, I've already shown a much more complex example in terms of that medical dipole, but here these are all loaded and rendered and can be then exported. Of course, care should be taken, because doing this without thought can just mean you have a lot of triangular geometry, which is actually very hard to track in codes like GN4. And also there are various other things. So typically this triangulation as emitted from a CAD package is really not used for science. It's used for rendering. And so you can end up with needles and fans, so very thin or very wide triangles. And you begin to see that in this particular rendering of this cylinder, that you can begin to see some thin pieces. So Pyg4ometry also allows you to manipulate these meshes and run well-established algorithms on geometry, which you've gained from other places. So so we can load geometry in from lots of different sources. I've just done a few there. And then, okay, so I suppose one really important use case is compositing geometry together. And so here, this is where this global registry becomes very important. I could make two readers, so I could just read two pieces of geometry from two separate files. I can get the registries associated with those things, which contain the namespace. And then as long as we have an algorithm to disambiguate, so there's 100% overlap in the names because the files are the same. So there needs to be an algorithm which disambiguates, but keeps the files consistent and the information consistent. I create a third registry, get the world volumes from both of the different files, create a world in which to place the geometry, and then just recursive methods here to recursively place the volume hierarchy and materials and defines and optical surfaces across. So this is really a step in compositing those two things together. Sorry, that's still running. Oop. Sorry, let me just evaluate this properly. Okay, so maybe I have, that should have, oh no, sorry, I commented out the line because that would have caused a crash. Okay, user failure. This is perversely not operating. Ah, sorry, okay, it is running. Yeah. So this is the cube geometry I showed earlier, the simple geometry with two world volumes, and those have just been absorbed and placed inside the geometry. But the file that we can write now, the names that on load have been disambiguated, and although they're appended with some other strings at the end, so a user can really tell, what detector, what piece they're placing, the parameters and so forth associated with each piece of geometry. Okay, so that can be done quite quickly. I'm not going to go through this because I want to get to the end of the presentation. There are a very simple method if you have a world logical volume in Pyg4ometry is to check overlaps. This then executes on the meshes, not on some more precise mathematical description of the geometry, and then you can quickly identify problems. So here I've done two cubes and I've overlapped them. And so the green is an overlap, and then the red is a protrusion from the world volume. All of these will cause problems when running. So if a user's just quickly scripting some geometry, they can check the overlaps and check that everything is consistent and not causing a problem. Point to note here is a mesh is always an approximation of geometry. For example, a mesh of a sphere is not a sphere. And it's up to the user to make sure. It's a very powerful tool, but no overlaps in this does not mean there are no overlaps in the geometry. And finally, converting to other code. So if you have an API that represents the geometry, it's then very simple to read, in this case, the ring of boxes that I showed earlier, and then just convert this to FLUKA. FLUKA also has a global namespace. It happens to be Fortran and kind of quite integer based or simple 8-character strings, but the same global naming problem exists. And so there's a FLUKA registry, and that can be written to a FLUKA file, very similar API. So the FLUKA submodule has a writer that you add a detector, and then you can just write that. And then here, this is Flare, which is a FLUKA front end GUI for doing geometry. And with that, we're able to create a runnable FLUKA simulation from a GANT4 GDML description. It's very easy to go that way, to go from GANT4 to FLUKA. It's much harder to go from FLUKA to GANT4. And if anyone's interested, I can explain why. And so this is what it looks like. The 3 plots here are sections through the geometry, and this is a 3D rendering up in the top right. So this is actually quite complicated, because in FLUKA you have to cut out the air. In this case, this blue is the air, and you have to cut out the cube before you place the cube, and that's actually quite complicated. So you actually have to explicitly remove areas and fill it with a different type of material, and so it's quite a lot of work in that. So I'm just going to return. So I'm just going to end the notebook there. So there's a lot more which I haven't presented, and so I'm going to go back to the presentation. Right. So I'm just going to go through a few. These are hard to show as notebooks, so I thought I would just do them in slides. So this is a compositing example, where I've taken things from different places. And so this is a simple injector in my mind, a vacuum chamber, a gate valve, some quadrupoles, a dipole, and a Faraday cup, and just marked on there where I've got the geometry. So it's very quick to write a short Python code to bring this all together and then re-emit it as GDML. Did a parametric detector. So this is layers of silicon and end wheels, and did that. It wasn't very long, but it's quite nice to be able to play around. Here, I was really testing the capability of the visualization system, because it has a lot of variables, but the variables all propagate through the Python expressions to the final GDML. So if you wanted to change a ring radius or something like this. With that, we have now GANT4 GDML to ParaView, which is used for other people. So this is Cedric Hernelsteins, who's at CERN, who's looking at a proton therapy system and is really interested in the dose. And so this is ParaView running on the right, and the dose is associated with beam loss near this wall, and you can see that overlaid with the geometry. I've showed this example before, more complex CAD loading. So I'll skip that. I work on an experiment called LUXI, which is a strong field QED experiment. And it's just at the end of the European XFEL, and it's a laser electron beam interaction system to probe the Schwinger limit and nonlinear quantum electrodynamics. So the top is the PyGeometry rendering of a rather complete detector. It looks like a beamline, but really it's a stretched out detector along a beamline. Did this conversion, and you can see the FLUKA rendering. So it takes a couple lines. And then the bottom is a fluence plot, I think, of electromagnetic energy being dumped. And so this is a section through the geometry to show what's going on. But this entire process takes a couple minutes, and although has its own vagaries because of the way I've done it, it's very stable, reproducible, modifiable compared to ways that we would have done this previously. Things I've not shown: extracting features from geometry, cutting and clipping geometry, so advanced visualization. Also, the root loaders are quite straightforward, optical surfaces, and the rather fully implemented PyBind interfaces to OpenCascade and CGAL. So they're very complete for what a HEP or accelerator person might want to do. Okay, if anyone's interested, they're in the repository under tests. I'm just going to end with a few cool applications. So a model interface to HEP geometry has a lot of applications, right? So simple interface to high-end rendering. So I'm thinking here OSP ray, physically based rendering. Simple interface to multi-physics code. So once you have the mesh, you can emit a mesh which is good for viewing in something like ParaView or Visit, but you can also send to console and ANSYS. It's an easy interface for testing new techniques, whatever that might be, optics or Mitsuba. for accelerated optical transport, say dark matter detectors. And it's maybe a little bit of a closer connection between engineering and HEP. Something I didn't mention is I can actually write the GDML as step files. I wouldn't use this as a data exchange method, but maybe it's good to send to an engineer and say, hey, here's a CAD file which you can load, whereas they probably wouldn't know what to do with the GDML example. Other fun things are, this is a GAN4 example of geometry. Excuse the whiteness of it all. I couldn't work out how to color it. So this is not a video. This is actually the 3D model inserted into PowerPoint. So this gives us the ability to discuss detectors. So this is what's called a GLTF export. So GLTF is a relatively modern 3D format, and so we can begin to put our models and our discussion of our detectors inside of presentations and have them in web pages. Just to show that I didn't. This is Luxy again, and I did the same things, and I just got it pivoting here, and so this is the same thing. Just rocking back and forth. And finally, the GLTF export allows AR and VR applications. So this is a really simple example of a cone and a box in GAN4, and then just displayed using render kit, reality kit. Okay, so just to conclude, a few slides in conclusion. Toolkit's developed, responding to need over the last 6 years. Interface is not the most uniform. It follows GAN4 quite strongly. And GAN4 has multiple constructors and methods to do the same thing. Need to have more convenience methods for modifying geometry. But this I just write them as need comes along. Some more advanced Python, so dynamic remeshing upon parameter updates. Effectively, this is a cyclic dependency graph, so it's quite complicated to do, but I have some design ideas there, so that when you change something, it's immediately updated. A more Pythonic, or at least syntactically sweet interface to the parameters, and you can see that it's quite verbose in terms of string and representation methods for some of the objects, which should be clarified. So, but I suppose I don't know what a user might want to do, and I've been surprised at what people have wanted to do, and invariably it's a few lines of code. For reference, there's a paper which is published a few years ago. There's an online manual and code repo in GitHub. Conclusions and summary: you can do so much with a stable API and a small number of algorithms. Pyg4ometry is of utility to many people using Monte Carlo particle transportation. Collaboration always welcoming new people. Luigi, who presented yesterday for Legend, joined a year or two ago, and was a fantastic job in the continuous integration and deployment, and the scikit build implementation and the pip deployment. And work like this is beginning to sort of inform work in visualization and Monte Carlo tracking in GAN4. So with that, I'd like to thank you and say the talk's over.
Thank you so much, Stuart. So do we have anybody who has some questions or some follow-ups from this fantastic tutorial that we saw? Eduardo, please go ahead.
Hi there. Hi, Stuart.
Hey, Eduardo.
I couldn't resist to say hi in person since we know each other for 20 years or something like that.
Yeah, PhD students together
for a while. Very nice presentation. I have to confess I was not aware of this, but I understand indeed it's not meant as a replacement for DD4 HEP and some other business that we use, for example.
No, absolutely not. I would advise anyone working in a large detector collaboration. This is no way interfering with that. I think it's the stages before where people are exploring geometry and simulations, and they want to do that quickly. I think very much before. I think ultimately, when people are happy with the detector, they should write the GDML and then import it into DD for HEP, and then begin to use it. But really, it's a stage before then.
Yeah. No, but well, there are probably many things, but you also mentioned quite a few connections with other indeed formats. I think this is something that certainly, talking in terms of Python ecosystem, has been very useful. So this is something I would totally recommend that you continue looking into, so people have the flexibility, and if something is more adequate, then they can transform. Like, for example, in the story with the histogramming tools in Python was a particularly nice one, where people were paying very much attention on some algorithm, some universal histogramming interface, so that people can talk to each other, and in a nice way, and then you take the best of whatever world you want in the end. In that respect as well, and not to divert too much discussions here, have you been discussing in some other experiments? For example, you mentioned looks as a use case. Are you, since many things are generic, are you getting in touch with many people, for example, doing R&D or developing new experiments, younger experiments that have to do lots of small jobs that don't really have a full machine with a stack behind their backs?
Yes and no. So Luxy is my experiment I work on, because it's a mixture of accelerators and fundamental physics. It was a choice that I made, and there's a strong need for the dumps are fully integrated within the detector. So hopefully you see my cursor. Where I'm pointing now is a dump, and there's a lot of detector behind that, and there's a few more dumps. So then FLUKA neutron transport from the dumps is absolutely critical for getting this working. I'm not reaching out too much. I think there's a different set of tooling. I think I suppose my aim is not for adoption in various places. I know that a few people in the HCB were using it. There's lots of individual users that it's for their workflow. I think adoption, I don't think it's quite appropriate for a large scale adoption by an experiment. It's very useful. Luigi from yesterday is, legend, and maybe that scale, but there are various experiments. It works great for Luxy to do this particular task of conversion to FLUKA, where there's a lack of effort to simulate this. And so of course, we have huge amounts of expertise in GN4, but almost none in FLUKA, and we can build this moderately quickly. And so this literally saves 6 months for a collaboration to do this. We're doing models similarly for Phaser and other places, but there's no coherence to it, Eduardo. There's not a real plan. It was very useful for internally, and I think it's stable enough for external use. But it's not an ambition, I suppose. I think people are more than welcome to use it, but there's so much else out there, and different constraints given the longevity and of detector descriptions for bigger high energy physics detectors.
Okay, no, thanks. Fair enough. But in any case, like you said, people can always have a look, and if that suits them, so why not? Okay, thanks.
We have a couple more questions, and I will go in the order of who raised hand. I'm not sure, Graham or Jana. I was not checking out, but Jana, you were first.
Okay, thanks. Thank you very much. Very nice presentation. I come from CMS and I worked on geometry. My question is, why what we lacked really is debugging algorithms, placements of the geometry. Have you considered integrating something like adding an algorithm and maybe just provide a JIT compile for that?
An algorithm for overlap checking? For placement? Yes. So placing geometry correctly?
Yeah, not geometry, the volumes, because in our case we have lots of it's a very complicated geometry CMS, and it's not just logical and physical volumes, but also algorithms using multiple volumes and placing them in the correct sort of rotation and transformation. So debugging those algorithms is really, really difficult, because we need to run the full CMSSW to do that. And I was wondering, this nice light tool, if you have considered adding a feature of providing say a definition of algorithm where you can just say, I want to inject some say C++ code, which is possible, and then just deal with these volumes and place them.
Yeah, I hadn't thought about it. Yeah, absolutely. Yeah, I think taking a piece of code, wrapping it, or having a nice way of wrapping it to say have a harness to debug a few hundred lines of placement code, or 500,000, whatever that might be. Yeah, I hadn't considered it, but maybe ping me and we can think about it, because I think that it's a good use point, because it's not the whole geometry, it's just a component.
Yeah, exactly. It's just like
that was the intent, and I suppose this overlap detection is which I showed. Once we built it, then clearly shows you at least the ballpark, the zone of where you should begin to start worrying about geometry. It's not perfect for approximation reasons, but yeah, I think it should be no problem either via a JIT or just binding in with a little compile step some algorithms. I think the difficulty is all the other volumes and other bits to make that placement code viable. Yeah, so you need a lot to make the placement code viable in terms of all the solids and so on.
Yes, definitely. Thank you very much.
Thanks, Jana. Okay, next one, Graham. So
yeah, thanks. Hi, Stuart. Thanks for the very nice talk. I will not switch my camera on because I'm on mobile internet and it's quite flaky, but hopefully you could hear my question. You said that the interface that you adopted was very close to the one that Geant 4 has.
Mm-hmm.
I think if you look at the Geant 4 interface, clearly it was informed by what was possible in C++ at the time that Geant 4 originated.
Yeah.
Probably not what we would do today. And we've also been looking at Julia wrappers for Geant 4, and we did start to think about maybe having a more modern interface to the underlying Geant 4 package. And I wondered if you had thought at all about the same, or if you had some sense from your user community of what people might find a more natural user interface than the one that exists in Geant 4 at the moment.
I suppose I've avoided thinking about it explicitly because I didn't want any additional cognitive load on a potential user. So and I didn't want to write documentation. So I've been very strict. If it looks like the Geant 4, then great, and suspended those. The moment you just tidy up some of these things, I think you open up a lot of things that you'd like to fix. And I just had to resist that for personal reasons, since instead of creating what I think is correct. So, but I haven't done that much thought in it. I think what I would like to do is have nice mechanisms for effectively overloading the construction, so that the existing complete suite of Geant 4 Geant 4 methods can be there, as well as a superset, which is maybe slightly simpler and they're well labeled, so it can be tidied up. And so this is, I suppose, what I'm currently thinking of, trampolining to multiple constructors, and then having a slightly different set of construction that's maybe a bit more streamlined in some sense. Which
I think that's one of the things that we've noticed can be improved.
Yeah, but I'm not. I very explicitly avoided that in my own thinking, because I just will end up rewriting what is my view the right way to do it, which is probably undoubtedly wrong. Right.
Understood. Okay, thanks a lot.
Okay, we are almost on the it should be starting next contribution, but let's go for a quick question of Luigi. I suspect there is also Perry. You want to add something?
Yes. Can you hear me?
Yeah, we can hear you.
I'm going to be very quick. I just wanted to briefly follow up on what Eduardo asked at the beginning about the usability, let's say, of Pyg4ometry outside, let's say, an inner circle. I mean, all the recent work on repackaging and refactoring the let's say, all the packaging infrastructure it exactly goes into the direction of bringing this tool, let's say, make it available to the broader community. So I really do think that now, for example, it's very easy to install and it's very easy to download. I mean, it's complicated package. Okay, we are using also internally scikit build core for the interested developers here. So I think it's really, there was a lot of effort recently, okay, to make this usable to everybody. Of course, at the beginning was motivated, you know, by the necessity and the desire to have this tool being used also in the long term in the Legend collaboration for the developing geometries. But yeah, just wanted to add this comment. Okay.
Thanks, Luigi. Pere,
Yes,
you can
I
ask
will-
quickly.
Very quick. It's a
Thank-
follow-up from the answer you gave to Graham. If you are really following the GM4 way of building the geometry, did you consider to use one of the GM4 Python bindings that will automatically do that?
But it makes, I mean, here it's very explicit. It's just this is not a Python wrapper for GN4. This is API-wise similar to the GN4 construction, but only considering geometry. It would be a bit, you know, for me, those bindings aren't well developed. They're not in stable routine use, I would say. The object ownership model in GN4 isn't clear, therefore the bindings don't come out clear in something like PyBind 11. I think it's an active topic of discussion within the collaboration, as far as I can see. Here I'm avoiding this, you know, doing anything to do with a more complete set of GN4, and only considering geometry. So I've looked at them just trying to understand what the state is, because of course operating bindings with the GN4 with Python bindings to the geometry gives you a very complete run environment in Python.
Exactly. That you will gain the possibility to really run a simulation. Okay.
Yeah, but right now, you know, I think it may be different if people have great bindings to their application, which is based on GN4, and therefore their application can have a stable interface, binding interface. This is what I've done with my accelerator codes. So I do have this already, but with my version of GN4, my application of GN4. Okay, I'm already over time.
Okay.
So
No, thanks very much.